Okay, in this video, I'm going to start by just motivating the definition of I, square root of negative 1. So I guess historically you might say the first most natural numbers to consider were what we call the natural numbers. The set of natural numbers, by the way, is denoted by this little kind of blackboard bold N. You know, you can't do bold on a blackboard, so you do it like this. In any case, those are the numbers 0, 1, 2, and so on, so all the counting numbers. The problem is, if you encounter an equation while you're figuring things out of the form 5 plus x equals 3, just as an example, how would you solve it if all you know are the natural numbers? You can't. I mean, intuitively, you would say, well, x should be negative 2. But if all you know is the natural numbers, you don't know any negative numbers. So that's how, I guess, historically they extended the notion to allow for the negative numbers. Zoom out a little here. So now that brings us to the integers, which we call z. Those are the numbers 0, 1, dot, 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 all the natural numbers, but also the negative 1, negative 2, and so on, all the negative natural numbers too. So that's collectively forms the set of integers. Okay, so now we can solve an equation like 5 plus x equals 3 because now we know what the word negative 2 actually means. That's the set of integers. Okay, but now if I give you an equation of the form 5x equals 3, and I guess historically these things actually came up, you know, for whatever reasons, money and so on. But the point is that if 5x equals 3, the problem is there's no integer x that I can multiply by 5 to get 3. So there's no way you'd be able to solve that equation. So you keep having this limited concept of number, and it prevents you from solving certain equations that arise naturally. So what you do is you invent these things called the rational numbers. These are things which are quotients of integers. A is an integer, B is an integer, you take their quotient, and we call that the set of rational numbers. And it's Q. I'm guessing Q stands for quotient, N stands for natural, Z, I'm sure, stands for whatever German word, you know, takes the place of the word integer in English. So usually if you don't understand why there's a letter being used, it's because you don't speak French or German, and that's the problem. But anyway, so if you knew what the rational numbers are, then you would know what a number like 3 over 5 actually means. It's an integer divided by an integer, right? So if you know what rational numbers are, then you can certainly solve things like 5x equals 3. Okay? But if all you knew were the rational numbers, again, I could ask you, well, how do you solve x squared equals 2? I mean, that's not hard to come up with where that might arise in nature. You have a square. Its area is 2. What's the length of its side? Well, I don't know. What do you square to get 2? There's no rational number, and hopefully you've seen this in a previous class. There's no rational number that you can square. There's nothing that's expressible as the quotient of two integers that you can square to get the number 2. It's a very pretty proof, one of the first proofs you've ever seen, I imagine. So you invent irrational numbers, these broader class of numbers that's called the real numbers. So that's the rationals, and these are the real numbers. So they include things like the square root of 2, and they also include extra things like pi and e and all these other irrational numbers as well as the rationals and so on. But still, if all you know are the real numbers, and that's probably more of where you guys are right now, you're only really familiar with the real numbers, how do you solve an equation like x squared equals negative 1? You square a real number, you're going to get a positive number, or 0. 0 squared is 0. But aside from that, even if x starts out negative, multiplying it by itself cancels the negative, you get something positive. How on earth are you ever going to get negative 1? So you extend the notion yet again. Each time, you know, historically, you invent these new numbers. Alright, so you can just invent something called I, this new number little I, that obeys the property that squaring it gives you negative 1. Now, at this point, I mean, it should seem kind of a little unfair. Like, by the same reasoning, can't we just divide by 0? I mean, okay, you can't divide by 0 now, but couldn't we invent a number that allows us to divide by 0 and all sorts of other crazy things? I mean, have we just thrown away all rules in the world? And the answer is no, but let me explain exactly what's going on. In mathematics, you can define anything to be whatever you want it to be, honestly. You can invent something called I obeying I squared equals negative 1 if you like. But, and here's the real interesting question, can you extend the traditional notions of addition and multiplication and so forth, subtraction, division, and so on, in such a way that the standard properties of arithmetic are still true? So if you decided to divide by 0, let's see what happens. Let's pay attention to what's going on over here. You can't divide by 0 because 0 times 5 is equal to 0 times 2. Well, they're both equal to 0, right? But if you were able to divide by 0, then you could cancel these two zeros, and you would get that 5 is equal to 2, which is, of course, a completely absurd statement. 5 can't equal 2. So, and this is just one example, but have fun. Show all of the different algebraic properties collapse if you allow yourself to divide by 0. So why can't you divide by 0? Well, you could define it to be whatever you want to be. I mean, you could define 1 over 0 to be some new number, or you could define, heck, if you wanted to, you could call it pi or something. I don't care. You can call it whatever you want. The question is, once you've defined these sorts of things, do the traditional properties of algebra still hold? And there's no way you can get them to work. There's a reason that mathematicians don't know how to divide by 0. It's not because they're stupid. It's because it can't be done in a reasonable way, in an interesting way that extends the traditional ways we have of doing these things. But luckily for imaginary numbers, you might think the same thing. Well, how do we know introducing I doesn't screw something up horribly? Actually, it pretty much works. I mean, you can multiply complex numbers the way you would, or imaginary numbers the way you would think to multiply them. I mean, if you say, well, what's 4 times I times 8 times I, or something like that? Well, it's just 4 times 8 times I squared. I squared is -1, so that's just 32 times -1, which is -32. It all really works quite well. You can even add a real number, like 4, to an imaginary number, like 5i. By the way, imaginary number means I, the square root of -1 that we introduced, times some number. When you add an extra real number onto it, we'll call that complex. I'll mention that in a moment. Alright, but it mostly works. Most of the properties of algebra still work. You have you can distribute. What are some of the properties of algebra? I'll leave them to you. I don't want to go over it in great detail, but a times b plus c should equal a times b plus a times c. Multiplication should distribute. A times b times c should equal the same thing as a times b times c. Associativity. Commutativity of multiplication, a times b. I don't need a parentheses here. A times b should equal b times c, and so on. I mean, you can just go pick up an algebra book, look at the basic properties of arithmetic, and for the most part, most of them work, even if you allow the numbers a, b, and c, and so on, to be complex numbers. Real numbers plus another real number times I, times an imaginary I. Not everything works. I do want to be a little bit careful here. Let me give you an example of one of the algebraic properties you're used to that does not hold when we start talking about imaginary numbers and complex numbers. So, for example, if you take the square root of -2 times the square root of -2, and remember, we were in a world where you're allowed to take square roots of negative numbers, apparently, then you would say, well, on the one hand, that's the square root of -2 times -2, or -2 squared. But doesn't square root cancel with squares? So that should just give you -2 here. On the other hand, if you actually expand it, -2 times -2 is 4, right? 2 times 2 is 4, and the negatives cancel. So that should be the square root of 4, which should just be 2. So you end up with something absurd. The -2 should equal 2. Well, that doesn't make any sense. Not all properties still work. The square root of a times b is not the square root of a times the square root of b anymore. This still works when a and b are positive real numbers. And by the way, it also happens to work when a is equal to -1. That is to say, when one of these things is actually I, it still works. And b is positive, right? So I've shown you an example here. The square root of -3 is indeed equal to the square root of -1 times the square root of 3. You can break it up, as long as one of them is I, as long as it's the square root of 1, right? Because that's what we were calling I. So that would be radical 3 times I. So you can think of this either as a name for such a thing. The square root of -3 is called I times root 3. Or you can think of it as breaking it up into the square root of -1 times the square root of 3. and it works in this way. So this property works sometimes when one of them is I, or if they're both positive, which is something you're used to, but it doesn't work all the time as we've seen here. Still, most of the basic properties work. It's just roots get a little fuzzy. I just wanted to give you that example. So now some terminology, just has to be said. Numbers of the form b times I, where b is a traditional real number, are called imaginary. Numbers of the form a plus b are where a and b are both real, so an imaginary number plus a real number is called a complex number. And this is complex analysis, so that's what we're going to be interested in. It's complex numbers. And the set of all complex numbers is denoted by this kind of blackboard C. So natural numbers, 0, 1, 2, and so on, are denoted by N. Integers, negative 2, negative 1, 0, 1, 2, and also on. Those are Z. Rationals are Q. Those are quotients of integers. Real numbers R. And finally, we've introduced the complex number C. And they're all nested. They're all contained in each other. N is a subset of Z, which is a subset of Q, which is a subset of R, which is at last a subset of the complex numbers. Right? How do we know that R is a subset of the complex numbers? Real numbers are in particular complex numbers. Complex numbers are things of the form A plus BI. Well, what if B is 0? Right? If R is a real number, then R plus 0I is equal to R, right? I mean, you're just multiplying by 0, you're adding 0. So this is a complex number. So in particular, we can think of real numbers as complex numbers, and we can think of the real numbers as a subset of the complex numbers. And then finally, I just want to highlight some interesting properties, just to get you familiar with some of the properties of I, the imaginary unit. If you square it, it's equal to negative 1. That's the way we defined it. If you multiply, let me switch colors here. If you cube it, then we can break that up as I times I squared. I squared is negative 1, so that's just negative 1 times I, that's negative I. If you take it to the fourth power, that's I squared times I squared. Negative 1 times negative 1 is just 1. I to the fifth power is I times I to the fourth. We just said I to the fourth was 1, so that's just I times 1, which is I. And I to the sixth is I times I to the fifth, which is I times, well, we just said that I to the fifth was the same as I, right? So that's I times I, which, again, I squared is negative 1. And it continues on. So hopefully you get the pattern here. We start with I, we multiply it by itself, we take it to the second power to get negative 1. We take it to the third power, and we get negative I. We take it to the fourth power, we get 1. And then everything repeats. When you multiply it by the fifth power, you go back to I. Then you go to sixth power, it's negative 1, then negative I, etc. It just keeps going. Okay? So in general, the rule is, for those of you who know what mod means, this modular arithmetic, I taken to the nth power is the same as I taken to the n mod 4 power. You just have to divide by 4 and look at the remainder, and that's the same. So like 6 is the congruent to 2 mod 4, right? So taking I to the sixth power should give you the same result as taking I to the second power, because they're congruent mod 4. And for those of you who know about groups and remember enough from group theory class, those numbers 1, I, negative 1, and negative I, they actually form a group. They're closed under multiplication. So they form a cyclic group of order 4 under multiplication. And if it's cyclic, it means it's generated by one element, and it's generated by I, by the number I. So that's a pretty nice picture there, and I guess that's all I wanted to say in this video.